Everyone, we're going to start with the first talk in this session from Felix Chung on Scalable Data Science in Python and R in Apache Spark. Once again, if you have any questions for Felix, we'll be holding the Q&A through Twitter, so tweet at PyData Seattle, preferably towards the end so it's easier for me to find, and we'll do the Q&A then. So thank you, Felix.
All right, thank you. Sorry, I'm still setting up. Let's give me a sec. All right, good morning. I'm Felix. I'm going to just jump into it because I have a lot of material to cover. I'm Felix, I'm principal engineer at Microsoft and Apache Spark committer. So today I'm going to talk about a bunch of data science stuff, but before we go that, I'm going to talk about just a quick introduction about myself. I am Apache Spark committer. I've been contributing to Spark for more than 2 years now. I'm a co-organizer of the Seattle Spark meetup, which is local here. Welcome to kind of join and check us out. We have a lot of interesting session. And I'm also the teaching assistant of the first massive online course back in 2015 about Spark. There are 2 of them. There's actually a bunch of more now, but back in the day, that's like brand new. And I also present at several meetup and conferences. So before we dive into the content, one quick disclaimer. So what I'm going to talk about today is largely contributed by the community. In fact, several different communities as we talk about several different pieces, how it fit together and how it actually integrated with Spark. So quick agenda for today. I'm going to do a quick introduction about Spark and PySpark and SparkR. I'm actually going to touch on how Spark fit into the whole machine learning puzzle here. And that's important because before we dive into talking about PySpark and SparkR and how you can do machine learning or deep learning on it, you kind of want to know why you're doing it this way, how all the pieces kind of fit together. And then we're going to touch on the built-in machine learning API that is available in Python and R. And we're going to talk about how you can use existing infrastructure and talk to some of these packages you're familiar with and leverage it to do machine learning or deep learning. So I'm going to talk about how machine is going to take over the world. Actually, no. I'm going to talk about Spark today. It's kind of not as exciting, eh? Can I ask for a quick show of hands, how many of you actually know what Spark is? Okay, maybe a good quarter of it, And then how many of you actually use Spark on a day-to-day basis for the last, few months, for example? Okay, not as much. So hopefully this quick introduction could be useful. So you might have already seen this diagram, I don't know, several thousand times. But Spark is, what is Spark? Spark is this general purpose cluster management system, which means that it could be running different type of workload on this in a distributed manner on this cluster you set up. What's kind of interesting is it has over 1,100 unique contributor from the last few years over. It is very popular. Popular cluster system that you use for all sort of different things. So it has built in this distributed computing model. So it has a client, it has a cluster manager, it has a set of workers that manage, it has executor running on each, and then there's several tasks running potentially in parallel. And this unit of parallelism is called a partition. So these are kind of some of these key concept ideas that we'll come back to several times during this talk. So hopefully you at least have an idea what I'm talking about. So what are the ways to use Spark? So there are people, there are lots of different companies or people, engineers out there using Spark for several different kind of ways. You could be ingesting data either from like a reliable messaging system like Kafka or just reading from like storage. You could be taking this data and pass it through some sort of ETL process, right? Using SQL or using data frame transformation. And then you can leverage something like Catalyst Optimizer for optimizing your processing, leveraging Tungsten leveraging something like CBO, which is new in 2.2 and 2.3. Or you could be, in the end, passing it through to a distributed machine learning kind of pipeline. And we, of course, we're actually going to be focusing on the very last part here. And we'll talk about kind of two, potentially very high level, two different approaches, how that works. So let's sidetrack a little bit, talk about the two language bindings. So language binding in this case, in this sense, is like Python and R. So let's start with PySpark. So PySpark is the Python API with Panda-like data frame that you can interact with. It integrates with pandas and NumPy. When you have to serialize a function or some closure capture that happens, it's done using Cloud Pickle. In terms of architecture, so you get the JVM pieces on the left-hand side. It leverages Py4j, using the Py4j gateway to interact between the JVM and the Python processes. And then it works with the remote process running on the cluster, the Spark worker, and then a bunch of Python processes managed by a daemon process. So the daemon process the daemon process kind of is the parent of all these actual Python worker. It does so by forking these Python worker as needed. And then we're going to talk about R a little bit. Spark R is the R language binding for Spark. It exposes functionality using something similar to a deployer, our deployer package. It has REPL, and it can be loaded as packages in IDE like RStudio. Architecturally, it's very similar to Python. But instead of Py4j, there isn't really something that we could use in R. So there is a proprietary, complete different implementation of this serialization and communication using socket through something running in the JVM called our backend. It also have a bunch of helper running in the JVM for somewhat complex type of things like building an ML pipeline we'll get to in a bit. But at a very high level, it's very similar. So you get the JVM process, you get a bunch of executor and worker running, you get our process running on the right-hand side. So the interesting thing about Python and R in this architecture overall is the fact that most of the work actually is executing in the JVM itself. These wrapper classes are operating in those languages, but then most of the heavy lifting is actually done in the JVM. So in this case, you can leverage all these optimizations being done in Spark in the JVM process, like predicate pushdown, code generation, all these new things that happens there. This is a benchmark from actually a long time ago, but the idea here is show you there's basically no performance penalty running all these different language binding on top of Spark itself. And the important thing here is this is actually going to be a recurring theme for this talk that we'll come back to a couple of times, that we want to do the heavy lifting in JVM. So where is Spark fit in on these machine learning puzzle? So like I said, I want to kind of dive into a little bit so that we have an idea going further into talking about the packages and all these ML pipeline APIs and how that works. So imagine you have an end-to-end data machine learning pipeline. You get a bunch of data from somewhere, maybe from data stream. You ingest them. You probably want to do some pre-processing, cleaning the data a little bit, deleting some of these kind of garbage data, doing some ETL, maybe aggregate it or join it with something else. And then you pass it to machine learning, whether it's creating or training a model or maybe doing predictions as we go. And then some of these insight, you want to be able to serve it and connect to something else. So why do we even care about Spark then in this case? Can we just do it this way? Like we can ingest it, we can run some ETL in some separate process, put it into storage, and then just run some like analytics job or maybe a machine learning job separately, right? All that stuff will work. Well, of course, this is going to work. But one of the kind of the recurring thing that I've heard a lot about is Sometimes you want to, you have some existing workflow already in Spark. Spark is really good with like ETL, with all these optimizations that are happening. Sometimes you want to be able to do this in one single application, right? Sometimes you even want to do it in one single language. So you want to be able to do this ETL in Python and then pass it to some machine learning library and things like that. Sometimes you want to be able to, sample the data or aggregate it, do some kind of massaging of the things before maybe feature generation, before passing to machine learning. So you need to do some heavy lifting on maybe a really big set of data that you have. And then sometimes you just want to run things at a scale, right? Things in parallel many, many times. So doing it in several different jobs is possible, but it's kind of error prone. It's a lot of coordination that needs to happen. And it actually increases the iteration time, by having to okay, let's get somebody to kind of do this ETL here, dump the data here, and then come back and do some more. It takes maybe weeks to do something. So sometimes it makes sense to do everything in Spark. So for instance, right, when you look at, let's just say you have ingestion in Spark and you have ETL in Spark, you have your machine learning here, using the ML pipeline model you can build in Spark in Python and so on. Maybe you do some iterative kind of things with the ETL, like do different, aggregate the data in different level to see how it works. And then at the end, you serve it and kind of write it out to some, persisted in some kind of key value store or maybe NoSQL database or something like that. But the serve part is kind of outside of Spark. So you see the gray box here. Or maybe you use something else to predict do prediction on the new test data coming in using something else, right? So you can write out the model that way. So another variant of that is perhaps not only you train the model this way, but you can also have maybe even the same job or separate job that takes the model and then do prediction and then serve it. So that's one approach. The other approach is, well, what if I have all these massaging and ETL and all that stuff, but then instead of doing everything in Spark, I want to do it with the library that I love and trust and I know of that I want to use and I think is superior and so on and so forth. So you can then break your data into pieces, right? And then run all these machine learning, either model training in parallel, and then you can even do something like evaluate the model output in parallel, like see which one model has the best performance, basically. So this is another version of running things in parallel at scale. Another third approach is you may have actually trained your model in a separate special setup. Say maybe you need a GPU for it, or maybe you need to have a multi-core GPU, very expensive, running somewhere to train a deep learning model, and this is somewhere in there. And you don't want to be doing this in the cluster. So you might take this approach of pre-training the model. You ingest the data, do your ETL processing and so on, take that data, and then run the prediction using Spark, for example, and then just serve it again in the gray box with something else. We're going to explore each of these a little bit. So let's skip to PySpark. So PySpark or data science. Before we start, let's talk a little bit about the Spark ML pipeline. What is the Spark ML pipeline? It was actually a relatively new thing. It was inspired by scikit-learn. So you can see a lot of these pipeline concepts is very similar to that. You can do pre-processing, feature extraction, model fitting, even do validation or evaluation. There are concepts like transformer, estimator, evaluator. You can even do things like cross-validation, hyperparameter tuning with something like this. So in other words, this whole pipeline captures the whole end-to-end sequence of stages and steps that you need for a machine learning job. So conceptually, it looks something like this. You have the input data frames of somewhere. You pass it through maybe a sequence of transformer, like tokenizing the text and do hashing, you do feature generation through these steps. And then you run it through a model, right? Logistic regression, which is an estimator. And in the end, you get a model that comes out of this. Then you can take this model to use it, to apply it to new data in a separate sort of pipeline. So Spark ML support a decent list of model. I won't say it's perfect. I mean, obviously it has a lot of trees, there's logistic regression, there's clustering. It has kind of decent coverage on almost a lot of things. But one thing you might notice is even though we have multi-layer perceptron here, MLPC, it lacks other neural network like CNN or RN or LSTM or any kind of fancy, anything that's slightly more fancy here. So generally, it is actually not the goal for Spark to have all sort of machine learning model support built in. So this is how where this talks and what we're going to be talking about kind of fits in. So but before we go there, let's just say you have a a bunch of text you want to kind of see and analyze it a little bit. So you tokenize the text, you hash it. It's kind of the same pipeline we looked at already, but this is the code. And then you set up the pipeline using these stages you can specify here, right, in the order that you want. And then you can use the pipeline to train this model that you have here. And then the model can be applied to test data and then do prediction as a result. So aside from the Spark API, you can also use it to plug into other pieces, how we integrate other packages and so on. But before we go there, all this is kind of mostly inspired by this paper in 2012 from Jeff Dean and all, talking about large scale. It was talking about deep learning. But the key concept here to extract out of this is the idea around model parallelism versus data parallelism. So Spark could be used as a scheduler. This is a term that comes up pretty often now these days. So the idea is you take Spark, and you have the data, you do your transformation, but at the end, you remember the diagram we look at, and you pipe it through other external, most likely native packages somewhere. You can use it for data parallel tasks, or you can use it for distributed execution with the same set of data, but executing, training a model in parallel, for example. So UDF is actually a great way to do that. But before we dive into how UDF could be leveraged or something similar UDF could be leveraged, let's explore a little bit about UDF. So there's actually several different ways you can use UDF in Spark. You could actually register a function, either anomalous like a lambda function or an actual function itself. And then that would be available in like SQL, in a SQL query. Or you could actually just kind of pipe it through like a math function or a math partition. The interesting thing about this is UDF is mostly a one-to-one thing. Basically, it takes a row, it applies UDF, and then it gets something, one row at the end out of UDF, except for map partition. So this is something to make a note of. So that's generally, the way this works in PySpark is something like this. You have an executor, you have a worker here, you get a partition. That whole partition gets serialized into something called a row batch. This whole thing gets sent to the Python process, right? Because there's still two different kind of processes running, like this JVM, there's a Python process. And each of these rows get pieced out and then sent to UDF for process, and then we expect to get a row out of this as well. And then all the results get serialized back in a batch and sent it back to JVM. So the rows are executed in sequentially. So something to consider, obviously, this is a lot of overhead. Not only are you sending a bunch of data around, and it takes time to do it, and it also needs to be serialized, packaged, pickle out, and everything. And there's additional overhead with multiple different languages. And then one thing to know is because you're sending things one at a time, it actually takes quite a bit of time to actually do, run UDF. So the good news is there are actually several different initiatives in the community to address that. Something like Apache Arrow, which is in memory columnar format, it does the same thing like a row batch, except the row batch actually get exposed directly to the native code, so you can actually have access to the entire batch instead of one row at a time. It does things like zero copy. In the future, it could do IPC, which means that potentially that would be a real zero copy in the sense that you're actually not sending things around that much. There's another Jira and Spark talking about vectorized UDF. So that's kind of something to look at in future. The reason why I talk so much about this is that as we look at native packages and how we integrate with Spark and all these other things. This will come up time and again, how data is going to be transmitted and so on and so forth. So that serves as a kind of the basis of kind of some of the future things we're going to be talking about very soon. So, but to begin with, in the early days in 2016, there's a package, there's a library called Spark sklearn. The idea here is to support running scikit-learn module in parallel. You can use it for training, either a single node parallel processing, or very seamlessly taking that and making it running on a distributed cluster setup. Unfortunately, really what it really does really well is just two things: grid search and gapply. Gapply is a very interesting concept. So the idea is you can organize your data in groups and then look at the group as a whole together. That actually is going to come back again, so make a note of that. So there are obviously some other newer things. I'm going to explore several of these new ones or maybe popular ones. I won't be able to actually cover everything under. I will actually have a list at the end to talk about several different kind of either machine learning or deep learning framework available. But something like Caffe on Spark. The interesting thing here is it's deeply integrated in each of these executor. It has optimized execution with GPU, running in the executor here. And it does interesting things like using LDMA to sync model across all these workers outside of Spark itself. So here's an example of what it looks like. One thing I want to actually highlight is what you see on the top here. So you have your predict caption function using Caffe on Spark to do all these other things, but you are the one responsible for taking your data set and doing a map partition on it. So that's actually why we talk about map partition is the way to avoid, to make it more efficient about transmitting data to native code, you really want to do something like what map partition is doing. And there are things like BigDL, kind of really similar architecture. It does similar things like a peer-to-peer all reduce and using block manager as a parameter server. It integrates deeply with the MLK library, anyway. So it does do things like reading other model and leveraging model that is generated, so something like a transfer learning type of approach. Like I said, you can also use block manager is the parameter server, so you can leverage that as well. And here's the way that you would potentially use BigDL for like a CNN. So in this case, you have the MNES data set with the handwriting digit here. And you can build a model like this. So what kind of looks very similar, you can see on the lower right-hand side here, how you can build an optimizer and you can do predict. And it's kind of really similar to the Spark ML pipeline. But the idea here is you just need to pass in the data set RDD in the training data in the C in the middle here on the right-hand side. And everything else is taken care of for you. So you don't have to do the whole partition massaging and all that stuff. There's another relatively new one called MML Spark. It's kind of hard to remember how many M's. I usually type 3. So this is the Spark ML pipeline model. It has enhancement like supporting Reacher type like images and text and so on. It also does deep learning with CNTK under the cover, do kind of fancy things like, hey, you can do training on a dedicated GPU node and then transfer the knowledge, transfer model into your cluster and so on, and do things like transfer learning that way. So it leverages map partition underneath the cover, and it does all these things very similar to the Spark ML pipeline model, as you can see on the right-hand side in the sample code here. And then there's TensorFrame. TensorFrame has been around much longer. It does things like hyperparameter tuning. It also can apply a pre-trained model at scale. It does row and block operation on TensorFlow. One thing that's interesting about this whole design or implementation is that it does direct operation to native C++ code directly from JVM, bypassing Python compiling. So here's an example of what the code looks like. I won't dive into the detail, but the highlight is actually the last line. You can see here, you can directly operate on the data frame. You can do aggregation and sum, and then you can pass it to a tensor frame using a call like map blocks that apply that whole transformation on the block of data itself. And then there's this new thing called Spark Deep Learning. This is, in fact, just announced a couple of weeks ago, back in June in the Spark Summit. It leverages the previous tensor framework. So that's why we talk about it in this particular order. It has similar Spark ML pipeline model. It handles things like it has support for image data, for example. And you can do things like DL featureization, transfer learning. One thing kind of interesting about this is you can actually take the model and then apply it as a SQL UDF. And then there's a future plan about hyperparameter tuning. So here's an example, some example of what it looks like. So you can build a predictor and then do transformation like the pipeline model that we talk about. You can do, you can have a featureizer plugged into the ML pipeline directly. Or you can register a model that you built previously and then just use SQL to apply your model that way. And it does so using the TensorFrame map rows function internally, which translate to map partition as well. So in terms of the ecosystem around, like I said, there's actually many more that I can't cover. But these are the one that actually has the Python APIs. So there's DipDis, there's Caffe on Spark, and there's sibling TensorFlow on Spark. Things like a bunch of Apache project like SysML, HiveMall, MXNet, for example. There's a couple actually more prominent or interesting one, but they are like JVM only, and there's no Python binding and so on. So let's move on to Spark R. So remember this, we have this slide, we talk about Spark ML pipeline. So in R, this is actually done in slightly different ways. So you have a LDA API you see on the left-hand side. You pass in text, and you have some parameter you can configure. What it does automatically for you is it builds the ML pipeline for you. So in the JVM, once you call this function, it builds this pipeline model automatically. It creates this regex tokenizer and apply stop words, and then vectorize everything and then call LDA before. So it's kind of convenient to call this API. Other things like there are model operator you can use. You can actually take a look at the summary of the data you have. You can use this model that you built and then apply it to make prediction on new data coming in using the predict call. Or you could actually save the model that you train, maybe use it in other languages as well. Before we go further into understanding how Spark R works with the pipeline model, one of the key concepts here to understand is this OWL formula that is kind of unique in R. So the idea here is you want to be able to use a symbolic form to represent your model that you want to build. So the example here is you respond R, Y is model linearly by F0 and F1. So you can express your feature and your label and target that way. And this is actually, in fact, implemented as a feature transformer in core Spark, which means you can actually use this in Python as well. There are other syntactic sugar here for things like the label column is automatically indexed for you, and then term columns are automatically one-hot encoded, so you don't have to do extra work for massaging your data set before sending it into the machine learning model here. So here's an example of what it looks like. So GLM is one of the things that we actually implemented two variations of it. There's one that matches the R signature exactly, and then there's one that actually has additional Spark specific goodies and you can kind of tune and use. But in this simple example is basically the same, slightly different order of parameters and so on. But the core of this is what we talk about in our formula you see here. where you specify the model, the feature that you want, and to apply it to the linear model. You can also do things like multi-layer perceptron. You can define how many layers of hidden layers you want, and all these parameters you can tune. There's also my favorite, random forest. You can do regression or classification on it. And then these are all the APIs we talk about. But what if you want to do more than just the 13 plus, actually more like, I think more like 20 now, different models that are supported by Spark R. You can also use the native UDF support. So this is a relatively new thing. There's two approaches you can apply. And remember what we talked about gapply? You can actually do that in R as well. The idea is you take a data frame, you take a Spark data frame, convert it into a native R data frame, pass it to your UDF, and then we expect to get back a native R data frame back as well. So the way this works is similar to map partition, except that this is automatically done for you. For each of the partition you have, it gets automatically serialized into the R native data.frame, send it across the wire to the R process, to your UDF, and they execute, and then we expect to get back a data.frame back again, and they get serialized back to the JVM process. All that happened in parallel. So you have these, similar to the R apply function, we have a D apply function. It takes the Spark data frame, and you can specify this anomaly function here, and you can manipulate these columns and process it. There's a variation of this, so we're going to be taking back the native data.frame without having you to specify the schema of the output. So you can do whatever you want, and we'll get you the native data frame that you can play around with. So here's a deeper example of this. So you can take a dapply collect, and then in this case, I'm calling the R random forest function. You can specify, very similar to what we did before, you can specify a formula here. And then I'm going to predict on the test data set coming in. So the interesting thing about this is actually not defined inside the scope we were talking about here. This is a test data set that get captured because of closure capture support in Spark R, and automatically serialize and broadcast to all the executor automatically for you. And then in the end, we take the in prediction and send it back to whoever is calling this. And then we can evaluate the performance of this random forest. There are another way to do this. We talk about gapply. You can then say, hey, I want to take the Spark data frame, and then group it by this column that I have here. And then the UDF would get back similar things with data frame, except the data is already grouped appropriately with the grouping columns. You can apply more than one the way you want it. And there's a slight variation that is gapply collect. So a couple of considerations. Spark R right now doesn't support nested structure. There's also one thing to be keenly aware of is the issue with data skew. When you group something, you partition something, your data could be skewed towards particular partition. So what if your partition or group becomes too big for our process? So sometimes, or even Python, even in this case, right? So you need to be aware how your data, what is the shape of your data and what it looks like. And there's also the flip side of the problem. What if you don't get enough data or not having enough variety that you need to actually build a machine learning model out of this? And then we talk about performance, cost-wise overhead around serialization, data transfer, and so on. We talk about closure capture too, so something to be aware that you're not actually accidentally sending a lot of data around. And then managing packages like random forest or some other R packages is something that we heard a lot of feedback on. It's something that you need to be aware how to handle that. There's also one additional way to do this. So there's also L-apply support in Spark R. So it's really good for these embarrassingly parallel tasks. So when you want to do hyperparameter tuning and so on. The idea here is to take a native R list and then distribute it and process it in whatever your UDF is doing, and then we get whatever your UDF is returning and send it back to you. So here's a more concrete example of what it looks like. So I'm generating a list of cost value here, right? And then I'm sending it through this training function that I define here that's calling SVM. Similar R formula we've seen here. This is actually not part of Spark, but this is a native SVM function. And then you can call Spark apply like this. They will just parallelize the processing for you. And then you can figure out what cost value actually makes sense, generate the best performance. Here's another more concrete example. Unfortunately, it's kind of really hard to fit the entire thing in a slide. It's probably going to take like, I don't know, maybe 10 slides to fit. But the general idea here is you can do something like TensorFlow here as well. So this is actually the RStudio TensorFlow R binding that is released recently. So you can load the TensorFlow library. Unfortunately, it's kind of really similar sounding name, but this is the R library, which you can trust me on that. And then you can create this TensorFlow session, and then you can use it for training this data set. In this case, we're looking at the MList data set again for the handwriting, and then you can use something like a convolution neural network to train it. But for instance, you want to train it 20,000 times. It's kind of hard to do it in a sequence, right? It's probably going to take quite a long time to train all those. But what if you can actually leverage Spark for doing this in parallel and doing it in a distributed manner, right? So this is kind of the way to do that. One thing I want to touch on is, I won't go into the details of it. The goal here is actually making Spark R available as a package. What's kind of interesting, though, I do want to highlight is actually at the very bottom, what it means is you can, in fact, leverage Spark R to control the JVM. Not just any other JVM, but talk to Spark directly, calling into its method, calling into kind of the Spark context and all these things to control in more details. So the hope here is, the goal here is hopefully community can actually write more packages on top of Spark. There's actually a few already out there, and we're going to touch on that quickly. But that's kind of what we're looking at. So that's actually kind of wrapping up the R aspect of it. There's actually several different alternatives you might have already heard of. There's a Sparkly R from RStudio. XGO has deep learning packages that works with Spark, as well as the R binding. SystemML has a R-like API, but it's not quite what the next line is actually going to be. This is R4ML, which is from several months ago. It was just announced back in February, I think. It actually seamlessly integrates SystemML and Spark R underneath the cover. So this is, in fact, for example, one approach where a package could also depend on Spark R. And there's also something like Apache NMXNet, which also has an R binding. So to recap, you could also just let Spark take care of things, or you can call into packages. One thing you want to be aware of is to be aware of your partition, where things are, how things go. And there are many, many efforts here trying to make that kind of really efficient and talking to packages and integrating native code and that sort of thing. All right, thank you. That's it. I'm open up for questions. Thank you.
Thank you very much, Felix.
Yeah.
Just so everyone knows, it is 10:40, so if you want to get to another session, you have 5 minutes. Otherwise, please stay. So while I let...
Question here, should
Yeah.
we take some local?
And I will take questions for the next 5 minutes while people transition.
Go ahead.
I just want to say that this has been a great deal of excellent information about how to do scalable
Right.
experiments.
Well, thank you.
So would you be kind to share, the deck so that we
Oh yeah, of course. This will be part of the conference, part of the information there. And feel free to reach out to me for more information about how these things works and how do you leverage it. These are the information that will be in the deck. So when you find the deck, you can find me. And feel free to just input. I'm really, really open and happy to engage with people that are using Spark and so on. So, thank you.
So I'll kick
Yes.
off with a question.
Yes.
Obviously, there are a lot of frameworks for Spark, so
Yes.
a lot of ways to go on both Python.
Barely
and
touch,
R.
the
Barely
cover.
touch those.
Basically.
Do you have any personal preferences, or at least a good, or how about this? What's a good framework for either Python or R to at least get started with? It might be a little easier to work with and not quite, maybe not all the bells and whistles, but at least enough to at least get starting going without having to get bogged down.
Right. That is an interesting question. I mean, I think the minimum, what we kind of skip quite a bit is in terms of the data massaging aspect of this, right? This is slightly out of scope for this talk. But oftentimes you want to be at least getting some familiar with like how that data frame operation works. So,
Right.
so maybe you want to learn about pandas or Spark or our data frame, just kind of know how to work with us. But I'm kind of biased. I think you should use Spark R because I'm the primary kind of owner of it, and I love people using it. And I feel like, R is such a, huge community out there. But this is a PyData conference.
We welcome
maybe we should
everyone.
use
It's
Python.
okay.
So there's always the debate in Structure Python versus R, right? But Python actually has a lot of potential. So you can see here a good portion of this talk talking about how Python has all these high-level packages you can leverage to very easily kind of like, you can forget about the fact that you're using Spark at all. Just like, hey, I'm going to be doing a TensorFlow here, right? With some overhead, how do you get the data into the shape you want it? Oh, sorry about that. Yeah. And then moving on from there. So, I mean, I would recommend kind of starting from that. If you're already familiar with some of these packages out there, and start from something that you're already familiar with and something that kind of bridge into Spark. So.
Okay. Twitter's not refreshing the way I need it to refresh right now. So just
No question, that's good.
So while we let Olivia set up,
yeah.
I had a general question of just out of interest. What is the general balance in the community of like Spark users versus Python users versus R users? Is it like literally third, or just how?
That's interesting. So there's been a research done by Databricks, the people that kind of created Spark.
Big proponents.
Becoming establishing a company and so on. And they had a research in terms of from their customer base. I think they're talking about the same for Scala and Python, but about 10% for R. So it's kind of less on our side. There's actually quite a bit of Python user. It's interesting. But if you go beyond the Spark space, I would say, I mean, I've seen a number of research that says basically the same number of people using Python and R equally. And that's kind of why I structured the talk this way. There's kind of half and half of this.
Right.
So.
Well, once again, thank you, Felix, for the great talk. And
yes.
Give us a round of applause.
Well, thank you.
We're going to give Olivia 1 minute to get a little bit more prepared, and then we'll start the next talk.